Swayam Prabha. Digital India. Educated India.
For today's class, we are going to look at mathematical modeling, continue with our discussion, and specifically we'll see this Lagrangian formulation of dynamics of problems. Okay, so let's begin with the slides. So this Lagrangian formulation is basically a method based on energy. So you don't need to really worry about the free body diagrams that you draw in the case of Newtonian formulation. So this is purely based on energy, and we'll see how it is effective in many different cases. So internal reaction forces are not to be considered during this formulation. That is what it is important to see that. And then this becomes like very good tool for many different complex mechanical systems, typically like complex 3D robot dynamics with multiple links connected together. In fact, it can be applied to the flexible robotic systems as well, although we will not have it in the scope of this class, but flexible robot also that can be modeled by using the Lagrangian formulation. Then it's better than Newton's method in the sense of couple of things actually. So as I said earlier, these equations are based purely on energy principles, and the equations that you finally get are having some kind of a mathematical structure, which also will be there for the Newton's the equation obtained by Newton's method. Both are equivalent to each other. That is what is, there is a proof that exists, mathematical proof that exists, that both the methods are equivalent. But the kind of way the Lagrangian formulation gets derived, you get some kind of a structure, and that structure becomes an important aspect for the control purposes. So we'll see how and why it becomes important as we proceed. Okay, so first thing, okay, that we'll deal with the Lagrangian formulation of these systems, which are mainly the rigid body motion systems. Okay, so what are these rigid body motion systems? Mainly having all these linkages here are rigid in the nature, so that we can write the kinetic energy, and you don't have systems which are having infinite degrees of freedom. You have systems where the degrees of freedom are finite. For example, there are 4 rigid bodies involved with ground as including the ground, and only 1 degree of freedom in this case. Similarly, in 4-bar case, then in this there are multiple rigid links that are involved, and then there are actuators also. There is some kind of a mechanism that is get formed because of the placement of these actuators in different places. So this will have a different kind of a evolution of dynamics of the system. Okay, so there can be many different, so there are these 3 actuators you can see. So this is typically a 3 degree of freedom arm, and if you want to consider, you have this rotary degree of freedom also, which is the 4th one. Okay, so considering this, of course, this bottom to be stationary, so one can consider depending upon the needs of the problem of control, what are the degrees of freedom that are to be included for modeling. There are some other examples of these rigid body systems. Robotic systems, you have gear based systems. In camera you'll have some kind of a elements for gears and motors for motion of the lens. This is again a robotic system. Okay, Kawasaki robot for different industrial applications, things like that. So all these systems, okay, they can be very nicely modeled by using Lagrangian dynamics, and based on the equations that you obtain in some generalized form, a control can be proposed for especially the systems which are fully actuated kind of systems, okay, where all these robot joints, every joint has actuation, okay, no joint is left unactuated. Then you'll get nice controls that can be developed later. So the basic principle in which the Lagrange formulation is based on is a Hamiltonian principle, the Hamilton's principle. Now, what is this Hamilton's principle? It states that the evolution of a system between the two time points t1 and t2, okay, is a stationary point of an action functional. Now, this action functional is defined in this kind of a way. So you have an integral of a Lagrangian function here, which is a function in general of the states of a system Q and derivatives of the so states are basically Q and Q dots. Actually, Q are generalized coordinates, and their derivatives also will be coming in the form of states. And then it can be a general function of explicit function of time as well. So this Lagrangian is defined in specific way, which is like kinetic energy minus potential energy. So this is not a general function of generalized coordinates. It's a very specific function called Lagrangian of the system. Okay, so this is very important. So this is a stationary point of this action functional, which is based on this kinetic energy and potential energy. So in some gross sense, one can see that the kinetic energy. So for a system, say let's say example of pendulum. Okay, when the pendulum motion happens, typically along the path of the pendulum, what is happening to the energy? Can you think about that? You can see that the energy remains constant for the pendulum, like kinetic energy getting converted into potential energy, and vice versa at different points. For example, if the pendulum goes towards the end, the potential energy is maximum, kinetic energy is 0, so it becomes like stationary there for a moment. Its velocity is 0, and when it comes to the center, the potential energy is completely converted into kinetic energy, and it has a maximum energy in the center. Again, it goes to other side. Okay, so that's how the pendulum can see that the total energy in some sense is conserved along the path. And the same kind of idea is there in this form of like integral form that is there for the functional. So if you take these points t1 and t2 are two states of the system, say somewhere along the path of pendulum, one can say, okay, corresponding to q1 and q2 as a generalized coordinates, or q in the generalized coordinate in the case of pendulum will be theta or the angle of the pendulum. So between the two kind of thetas, you will have this functional, okay, defined, and now what we are interested is in finding the path between these two points of a system, okay, along which this functional has a stationary value. What it means is like as you perturb, say suppose instead of the circular path that we know of, we take some other path for theta. Not really, okay, sorry, the circular path remains the same, but in time, see this q is defined as a function of time here. Okay, so we take whatever function of time, some function of time for theta, okay, and that defines one path between the two theta points of our pendulum. Okay, but that may not be the final path. I mean, the pendulum has some kind of a sinusoidal variation of theta. So for let's say I assume for the discussion purpose a small angle theta kind of a variation. Okay, so if some path is linear that is defined, then that is not a path where this function will have a stationary point, in the sense like that this function functional is minimum. So what you mean by the stationary point is like, when you take a derivative of this, the derivative will give you with respect to q, or with respect to actually the curve q in terms of time, that derivative will be equal to 0. First derivative will be equal to 0, which will give us a stationary point. Okay, so that is a kind of a idea that goes into here. So you have many different paths defined for this evolution of q, and you choose a path, okay, in some way or mathematical. We will see what is mathematical way of doing that. Basically by using the Hamilton, the variational principles. You choose a path along which this functional is stationary, okay, and to come to that point, like, we'll need to take, like, partial derivative of or delta of s, or variation of s with respect to q. That will be 0. So variation of s with respect to q will be 0. That will give us equation which is the Lagrange equation. So we'll not get into the derivation part of this equation, but we need to have this like fundamental concept understood so as to see the applications. Okay, so for example, in this case, this L has only q dot and t, and the L is defined as kinetic energy minus potential energy. So if these q's are these are like generalized coordinates, and they are equal to the number of degrees of freedom. So if you choose q's in such a way that they are not matching the degrees of freedom of the system, then we'll be in trouble. Okay, so we'll have to kind of express the kinetic energy and potential energy in terms of these generalized coordinates. That is the most important aspect or point that one needs to remember. Okay, so we'll as we proceed, like, we'll talk a little more about this point. So what we are going to see is not a derivation of this equation, but application of the Lagrange formulation. Okay, so let's see what is the Lagrange equation that we get after, like, doing these variational principles applied to this functional to minimize for a general system of n degree of freedom kind of a system, how this functional minimization, okay, or del variation of del s, okay, variation of s, which is del s with respect to q's, okay, will be equal to 0. What it gives as a, when we kind of mathematically derive it in terms of L. So that gives us this final equation. Okay, so just see carefully, this equation states that this L here has a partial derivative with respect to q dot. Okay, so this is so L will in general be dependent upon q dots and time explicitly, but here when we take for example, it's a partial derivative with respect to q dot, and here, like, you have a partial derivative with respect to q, and then this is a full derivative with respect to time. So this is not a partial derivative. Okay, so this is important to note here. So as we apply this, things will become a little more clear now. And q, as I said, are generalized coordinates. So generalized coordinates will be equal to the number of degrees of freedom of the system, and if they are not, then there will be some constraints that would exist between the coordinates. So for example, if we talk of pendulum system, my favorite system, the theta is like a generalized coordinate we can take, but x and y coordinate, if we express kinetic energy, potential energy in terms of x and y, now x and y we know are not like independent of each other for pendulum kind of a system, because it is moving along a circular path. Okay, so that path gives some kind of a constraint between x and y. So then this particular equation may not be applicable. Okay, there is something else that we need to do in terms of if you want to use the coordinates x and y. separately. We can make a choice to express everything in terms of x or everything in terms of y, considering that it is moving along the circular path. Okay, that is okay, no problem. But if you want to use x and y separately, then that is not a good, that is not possible with this kind of a discussion that we are doing in the class right now. There is some other formulation called constrained Lagrangian formulation that will have to be employed for the case where we have x and y which are dependent upon each other. So we'll have to have additional constraint, that equation that is put, and then some constraint Lagrangian that needs to be defined, and then we need to apply the Lagrange formulation for a different setting. So right now we are looking at only a case where there is no constraint in the system and you have all the degrees of freedom are having independent of each other, as a definition of degree of freedom says, and your kinetic energy, potential energy are expressible in the form of generalized coordinates. Okay, these are some of the important considerations to apply for the Lagrange formulation. Okay, so the L is defined as a difference between kinetic energy and potential energy. So kinetic energy in general for a rigid body system can be defined, as you know, from the concepts of kinematics and dynamics that we have seen, is half m v. Now this v is of the center of mass of this C point is the center of mass of a rigid body. So you just see the rigid body motion in motion. It may be part of some mechanism or part of robotic system or part of whatever system, doesn't matter. We just see a center of mass and what is the velocity of, we ask a question, what is the velocity of center of mass of that rigid body, and the kinetic energy is defined as mass times v transposed into v for the center of mass. This vc is the velocity of the center of mass. Okay, so it's like a half mv square, but like generalized now into this form. Okay, for the rigid body, or like in general kind of a motion in 3D space. And then this is not a complete kinetic energy, this is just a translation part of the kinetic energy, and then you have this as a rotational part of the kinetic energy. Again, this we have seen in the like KDOM kind of a fundamentals. If you want, you can just just revise this kinetic energy expression, revise some of the fundamentals of kinematics and dynamics, and you realize that okay, oh, this is expression for a general expression for kinetic energy when you have a rigid body motion having it in the 3D space. And this omega transpose I omega, where I is the inertia matrix for the rigid body, defined along the defined about the axis of coordinate system passing through the center of gravity or center of mass of the body. Okay, so this is again another important point. Like you are not taking inertia, this inertia matrix about any other point in the system. So you are taking it about the axis passing through the center of mass of the body. So these are the two terms that are coming in the kinetic energy expression, and these inertias, these are mass moment of inertias, are defined in this kind of a fashion. Okay, so this is like a expression for general rigid body kinetic energy motion, and then we can use that into Lagrangian formulation. Okay, so we'll see now the application with some of the systems. See, potential energy, one can based on the some kind of a reference, one can define potential energy in terms of these different generalized coordinates. We'll see how this definition of kinetic energy can be then finally expressed in terms of some generalized coordinates and so on and so forth. And then we can do some generalization in the later part of this lecture or maybe the next lecture. Now we can see some simple examples for the formulation. So let's take our famous spring mass damper system here. So kinetic energy for the system is one can write very simply as half mx dot square. There is only one mass that is in motion. We are considering the spring and damper to have like massless properties as compared to the m. So this is all like this one has to think okay, what are our considerations, okay, what we are considering as degrees of freedom, what part of the system we are modeling, what is the dynamics of significant importance. These all user has to have that thing in the mind, okay. Or mechatronics engineer has to have very clear understanding, okay, oh, look, this is an important part of my system, that is what I want to model, and other parts I'll kind of ignore in the model. Otherwise, like you start thinking of, okay, spring also has a mass, or like damper also has mass, where is the kinetic energy, potential energy, or like because of these masses, or sorry, the kinetic energy because of these masses, which we have not considered here. So then like one can consider, of course, if we want to for formulation, but then whether it is really worth considering or not is a question, because the terms that you are getting in the final equations are completely ignorable as compared to this term which is coming because of this big mass. So that those kind of a calls is what user has to take, and then he or she has to go ahead and define these energies. Now look here, we are not really considering this damping in the system in any of these energies, okay. The potential energy, as you know from the first principles, that energy stored in the spring is half times k times x square. So we are not this C, or the damper energy is not coming in these two equations. So where it will be? So and then also this force is not coming into formulation of Lagrange equation. So these all terms, like these terms which are not coming finally in the energy expression, they have to get somehow considered in this generalized force along the direction of the coordinates. So this tau I is a generalized force along the direction of qi. Okay, this is a statement very important, because we need to make sure that okay, this force is along this direction. If it is not, then like we need to find out what is the force along this direction, okay, by resolving the forces in appropriate kind of a way. Okay, so say for example, if I'm applying this force to be in this direction, okay, that is what is given, then I need to see what is the component of this force which is coming along the generalized coordinate, which is x defined in this case, okay. So those are the kind of nitty-gritties that one has to be bothered about while applying this Lagrangian formulation to simple systems that we will consider. So then we define this Lagrangian as kinetic energy minus potential energy, and now you take a pause here and like see, derive yourself what is the equation of motion coming when you apply this formula, okay. So it's kind of going to be pretty straightforward, because x dot is coming here only, and then when you say dou L by dou x dot, okay, that time you get 2x here, 2x dot here, and then you differentiate and everything like that, okay. So you do that whole process, and then after doing, you come back, okay. So after coming back, you will see that okay, this equation is of the sort, this mx double dot plus kx is equal to, now this force F is in the direction of generalized coordinate x, okay. So in the direction of x, any other forces that exist would be bundled into this F here, and in addition to this external force F that is applied on the system, this C x dot damping also can be considered. So this this F can have value which is this F minus C x dot, okay. So that is a generalized force that can exist on the system. Right now I have ignored the damping and I have just written this equation only with this F here. Okay, so one can consider also the damping in terms of energy part, which is called Rayleigh damping function, but we'll introduce that later into the system. Most of the cases, like it is easy to see that the damping can be resolved in the direction of generalized coordinates and incorporated in the equation later as a external force. Either way is fine. So then we see some same system, but now if it is considered in the vertical plane, then how do you account for potential energy in this case? So it depends upon how do you define your generalized coordinate to measure from. So there are two possibilities. One is like you see that okay, your generalized coordinate x is defined when the spring is having zero extension. Okay, that is one kind of a case, and other kind of a case will be where the spring is having extension in such a way that the initial deformation of a spring balances the force mg. Okay, so for Lagrange formulation we can consider both of the cases, but then the energies that are to be considered then have to be a little different. So in first case, when you consider the spring to be having free length here, from that is my reference point for x to begin, then you consider like a normal way all the forces of like say now there will be additional potential energy because of the lowering of this mass. Okay, that has to be accounted for, and then you write the equations of motion in that kind of a form. That is the most what you say general way to consider. That's the best way to consider the derivation in you start off with the spring having a zero deformation. Okay, that's how like you should define. There should be no stored energy in the elements to begin with. That will give you formulation without any ambiguities. Other formulation where one can see that okay, if I deform the system, allow it to kind of get into the equilibrium position with spring force balancing the mass, then I define that as my zero, and from there I start measuring x. Then you know that from your Newton's formulations also, that then the additional change of the gravity, okay, or gravity force will not come into picture in the formulation because that initial balance of the spring force is already balancing the mass. So this then once that balance happens, beyond that whatever displacement is happening is exactly same as in the case of the horizontal version of the system. Okay, so I would suggest that you apply Lagrangian formulation for the case where like you have a free length of the system, and see the equations for yourself. And then if you have any doubts we can discuss more later. Okay, so you do that and then you proceed for the further recording.